So today I want to switch directions a little, not switch directions, but change the focus of stomata, and move from individual guard cells and what's happening inside them and their environment around them and what they respond to, and put them in the context of a crop canopy or some sort of vegetation canopy. And what can we say about the behavior of this canopy based on what we know about what guard cells are doing and what stomata are doing? And when I say behavior of the canopy, I mean, I'll talk in terms of water loss, transpiration rates, or CO2 uptake, net photosynthesis or net CO2 assimilation rate or something like that. What can we say about what's going on at the canopy level based on what we know about what's going on at the leaf level or the individual stomatal or level? So that's what I want to talk about. And so this is PowerPoint number 19, and I had it put it up on Tuesday. So if you downloaded it then, I've changed it a bit since then, and this is a newer version. It's very similar, but you know there are some changes. So, for example, this picture wasn't in Tuesday's version. Okay, but anyway, how can we determine water use of an entire canopy? I mean, that's a practical question, right? How much water is this crop using? And it's, for example, if we're irrigating it, how much irrigation water do we need to supply? How much water is being used? How much CO2 is being taken up by this crop canopy? What's the exchange of CO2 between the canopy and the atmosphere? How do we address questions like that? Okay, well, in terms of water use anyway, I can think of 5 ways, and I'll briefly go through the first 4 of these and spend hopefully most of the time today on the 5th one. So, how can we determine water use of the entire canopy? First, lysimetry, stem flow, canopy chambers, eddy covariance techniques, and modeling. So, lysimetry. What's a lysimeter? You know what a lysimeter is? It's a great big pot that you bury in the ground, essentially. That's what it is. You know, it's a big container of soil that you dig it out, put it in your container, and put it back in place. So now you have this monolith of soil surrounded by some sort of container. And what you can do, or what people, one of the ways these things, I don't know who comes in here and sabotages this.
They have it out for you, Doctor.
I think they do. You know, I'm sure it's not somebody here in class, right? It gets here before I did. I don't know what it is. I've never had this happen.
If I were to do it, I'd just shoot it over on the other side of the wall, so it'd take 5 minutes for you to like.
There you go. There you go. That's one way to slow down on things. Yeah. What you can do is put this big thing on a balance, some sort of a scale, so that weighs this entire volume. So here's the top of a lysimeter, and if you have a balance under there, then as this canopy uses water, it weighs less, right? And you can see on the balance or load cells or however you weigh it, you can get an indication of how much water is being lost by the change in mass from day to day, let's say. I mean, you have to consider if the crop is growing, you know, that's increasing in mass a little bit, but typically the mass change from the loss of water is way more than the mass change from what the plants are eating in biomass. So a weighing lysimeter is a way to measure the water use from a plant canopy. I mean, it's kind of, imagine trying to do this for your experiments, unless you have access to lysimeters someplace that somebody else has already done. It's not a very practical way of doing it. Also, you know, it's a pretty big task to put these in place, and you disrupt the soil tremendously when you do it. So after they're installed, you have to wait around and things like that. But, you know, very useful method. And at the West Central Research and Education Center near North Platte, or in North Platte, south end of North Platte, there are lysimeters in place. I don't think those are weighing lysimeters, but what they do have is, or had, is a way to collect the drainage that's coming through here out the bottom of this thing. So if you collect the stuff that drains out the bottom of this lysimeter, you can look at, you know, how much nitrogen is moving through, or any other thing you're interested in. So even though you may have a lysimeter that's a non-weighing lysimeter, it's very useful for doing these kinds of hydrological studies too. But lysimeters work. It's just not very practical for a lot of experiments.
How expensive is one?
How?
Expensive, like putting one in? And
Well, I think the expense, most of the expense is in labor. You know, even at our woefully low minimum wage in America, you're gonna pay a lot of money for just the labor, somebody's labor to do this.
But like the actual license?
The lysimeter itself?
Yeah.
I don't know, I've never worked with them, so I'm not sure, but, you know, it's gotta be in the thousands of dollars for these in place, I would imagine. But I think that most of the expenses in labor, not, I mean, this is just, there's nothing special about the lysimeter, it's just a metal container, you know, usually, or maybe plastic, I don't know.
We have them in our research group,
Uh-huh.
and they're only like a charcoal chimney, basically.
So, yeah, that's another adaptation, and we've used actually what we call mini lysimeters.
Mm-hmm.
So they're about this big around, you know, PVC pipe, 3-inch, 4-inch PVC pipe,
Yeah.
and just a short little thing. And you can use those, put them, well, the way we did it was to put them in place in the soil, take them out and weigh them each day. But, and then install new ones each time, because when you cut that piece of soil off from the rest of the soil, its water content and things are gonna change differently than the bulk soil. And so we would install these every day and weigh them the next day, and then install new ones. I mean, it works, and it's a way you can do it. But it's pretty labor intensive too. And in fact, with the mini lysimeters that we used, we were just able to put them in between the plants to get soil evaporation, not transpiration with plants in it. But I can imagine, yeah, you can have all different sizes with some plants.
Yeah, it seems to me the most expensive part of it would just be the probe and the data logger. But that's an uneducated guess.
I mean, you could get a data logger that would handle something like this for $1,000 probably.
Yeah.
And that's probably less than you're gonna pay for labor for putting in something.
Yeah, the labor is definitely the hard part.
So,
Our guy was out there like every day or every other day weighing.
yeah,
like,
yeah.
40 of them.
Yeah. And so, you know, that is a consideration, especially, I think, the smaller you go, is that the conditions inside this lysimeter may be different than outside of it. You know, that's why people like to use really big ones, so that they can sort of imitate what's going on. You know, inside here, maybe not that much different from outside, I don't know. And if it's deep enough, but if they're pretty shallow, then it's easier to get, to have the conditions inside those smaller lysimeters different than the bulk of the soil. But I mean, there are advantages and disadvantages for all of each of these techniques. And lysimeters have their place and they're used. You know, they've got some, I don't know if they call them lysimeters, but up at, what do they call it? NREC now, near Mead, in the horticulture area. There are some of these, I've never heard them called lysimeters, but that's essentially what they are. They're rectangular, and you can go down and look at the soil and watch the roots growing and things like that. You know, so they're useful that way for other studies as well as water use studies. But you need to be dedicated for installing a big system like this. Okay, another way to measure water use is by stem flow gauges. Stem flow. So here's a company, Dynamax in Texas, that sells these things called stem flow gauges. What they are is, I'll show you the next couple of slides some details, but what they are is a thing you put around the stem of a plant, like this tree, and hook it up to the data logger, and by doing things, it tells you how much water is moving through that stem. So you're connected to a data logger and measure all day long, and you can get the flow rate through the stem. And if you are judicious in where you place these, you can calculate, like for this corn canopy, the water use of a single plant. And then from those measurements, extrapolate to the whole canopy. All right, there's some advantages, disadvantages for this too. Let me go back one. Sorry. Here, this website, Dynamax. This is the website, so if you go here, products, they have all kinds of stuff. Soil moisture, maybe you've used these data probes. We've used these in the past for measuring soil water content. They have different probes for that. But this thing is called the Dynagauge Sap Flow Sensor. So you can go here, have a look at it, look at the brochure, look at the manual. And there's a lot of information about how these things work. Have a look at that website. It was started by, this company, Dynamax, was started by a fellow named Kees Van Babel, who taught at Texas A&M University, retired now. But, anyway, these things work by, or one of the ways these things work is by measuring the amount of energy you put into the system and then the temperature distributions around where you're putting that energy in. Okay, so this thing has a heater. Here's the plant stem, this green part. It's got a heater that encircles the stem, right? So, you know, inside here is a heater. And you can measure how much power you're putting into the system, how much energy you're using to heat up this heater. Well, what happens to that energy you put in? Some of it is dispersed radially out the sides of this heater to the atmosphere. Some of it goes down the stem like this, and some of that heat goes up the stem. And if you measure the temperature profile above and of the stem, above and below where you're putting this heat in, the temperature distribution, if there's no water flowing through the stem, you get, let's say, similar temperature distribution above and below this heat, right? If the thermal conductivity of the system is constant. But when water is moving through the stem, it takes some of this heat and moves it up. And so you get higher temperatures here compared to here. And based on those differences in temperatures, you can calculate a flow rate. So here's a series of equations that I'm not going to talk about that are consistent with this way of measuring sap flow, stem flow for a single plant or a single branch on a plant. And as I say, you can use this technique to quantify the water use of an individual plant in a canopy. Then if you know how many plants in a canopy, you can scale up that way, right? The challenge becomes you're typically limited in the number of these sensors you can deploy in a given situation, right? And so for our sites up at Mead, let's say 65 hectare field, what if you have 10 sensors? That's a lot of these sensors. What are you gonna do on 65 hectares? Which 10 plants are gonna represent that whole site? That's what I'm saying. Of this canopy, which of these plants is like the average one for this situation here? It can be challenging in how you deploy your instruments. Okay, so another way is to use a canopy chamber, right? So here's Jun Kim's chamber that he used when he was here in Minnesota. He used in Minnesota. Jun Kim got his PhD from Nebraska. When he was here doing that, he had a site in Minnesota that he used this big chamber in. And so this thing is maybe 2 meters by 1 meter by 1 meter. You know, it's like a big box, big clear box. You put it on the canopy. And just like I described for the leaf chamber, like the Lycor 6800 works, you can use a chamber like this to measure evaporation or transpiration from whatever's inside this chamber by looking at the vapor pressure going in and coming out and things like that. Turns out it's much more amenable to measuring CO2 fluxes than water vapor fluxes. And the reason is water sticks onto everything. It's difficult to find a substance that water doesn't glom onto, doesn't adhere to, right? Water is really sticky, a really sticky substance. And so if, say, the humidity is changing inside this chamber, or if the, let's say the absolute humidity is changing inside this chamber, water is either going to be coming from the air and sticking onto the walls of the chamber, or coming off the walls of the chamber and moving into the airstream. It's difficult to find substances that don't interact with water like that. Okay, so that's one problem, but maybe we can overcome that. Another problem with a chamber system like this is you're altering the environment of these plants by putting your chamber over, right? You're changing the wind speed, you're changing the radiation a little bit, you're changing maybe the humidity, depending on how long you leave this on. You're changing that environment. And assuming that you're interested in what's happening to these plants when your chamber's not there, it may be difficult to interpret the results from chamber techniques and apply them to the situation that exists when your chamber's not there. Here's a smaller chamber we used in Saskatchewan for some of these things, but didn't use it very much because they have a whole range of problems. They're useful, but as I say, they're more amenable to CO2 fluxes or maybe even methane fluxes or nitrous oxide fluxes than they are to water vapor fluxes. One of the things that's useful in what we did with these chambers is Teflon is very good. So they make clear Teflon. And water doesn't really stick onto Teflon. And that's what this chamber is lined with, Aclar, they call it, this one type of Teflon film that we use for making some of the. Okay. The other problem with chambers may be, like I mentioned when we talked about Phragmites, is that, you know, these Phragmites plants, at least if you put a chamber on this canopy, which one of our colleagues from Colorado State tried to do a few times, these Phragmites plants are connected, the plants inside your chamber are connected to plants outside your chamber. And what's that, and connected, I mean, you know, with airflow between them. And what influence does that have on what you're measuring, and how can you interpret what you're seeing, what your results are from your chamber measurements? Again, the situation with chambers. Not only that, but Phragmites, or let's imagine corn, right? Our maize gets up to almost 3 meters most years at mead, right? Up as tall as the ceiling. That's a big chamber. How are you gonna get that thing on the balance? So there was a guy, Dan Rajkowski, I think his name was, in Minnesota, that actually used big chambers mounted on a tractor, you know, and like a forklift or something, you know, like put them on these big maize canopies and made measurements like that. You know, you can do it, but it's got its own. So, okay, eddy covariance is a very useful technique. Here we go. Eddy covariance is a very, very useful technique for quantifying fluxes, like water vapor flux, CO2 flux, methane flux, momentum flux, all kinds of things. And with eddy covariance, you have, okay, so here's Jun Kim's setup. He worked with Shashi Verma, who I worked with, and that's why I was there. But here's a sonic anemometer, 3D sonic anemometer. Here's a different kind of sonic anemometer. Here's another sonic anemometer. But you measure the wind velocity, right? And decompose it into 3 orthogonal directions, right? X and Y. Well, what do they call it? UVW is how micrometric use UVW, the vertical component. So you measure the wind up here, and just adjacent to it, you measure whatever you're interested in. This happens to be a CO2 sensor, CO2 analyzer, an infrared, an open path CO2 analyzer that measures the CO2 concentration in between these 2 points. And it measures it very quickly. You have to make these measurements quickly, so typically they measure at 10 hertz, 10 times a second, or some people like 25 hertz, whatever. You have to make those measurements quickly, and what you do is correlate the vertical component of the wind with the concentration of whatever you're interested in, say the CO2 concentration, and correlate those, and then over time integrate those components to get exchange, you know, an exchange of, let's say, CO2 between the surface and the atmosphere, whichever way it's going. Well, this sensor also measures water vapor as well as CO2. And so we can use it to get fluxes of water vapor between the surface and the atmosphere. At this point, it comes with a set of assumptions, one of which is that the flux is constant with height. If you get far enough away from the canopy, the flux is constant with height, so you measure it here, or here, or here. It's not going to vary. The other one is that there aren't advective terms. You don't have water vapor coming in the side of this system, or CO2 coming in the side. And you know, that's, these are also used to measure, if you measure temperature, you can get sensible heat, what's called a sensible heat flux. And a lot of times, If you have a mass of, a synoptic front coming through, you could advect heat into the system, and that screws up what you're trying to measure, because it's an additional term that you're not accounting for in your system. But, I mean, all told, this is a state-of-the-art technique for measuring large-scale fluxes of water vapor, CO2, heat, and other components. It's being used more and more for methane fluxes. Nitrous oxide still in the future, because getting a nitrous oxide sensor that you can measure at 10 or 20 hertz is not easy. Methane, having a concentration of about 1 part per million in the atmosphere. CO2, okay, so water vapor being 2-3% of the air, there's a lot of water vapor to measure. That's fairly easy. CO2, 400 parts per million, that's pretty easy to measure with infrared techniques like this sensor. This is made by Lycor, right here in town. Methane, 1 part per million, it proved to be a challenge. In fact, this was one of the first sites to measure methane fluxes with eddy covariance. And the methane sensor is inside this climate-controlled box here. It's a big sensor. Now, Lycor makes a sensor like this, that's about this height, that is an open path methane sensor. This is a closed path. TDLS, tunable diode laser spectrometer, is what was used. And this part of it, just to measure the methane concentrations, was about $250,000 back in 1990. Around there. So it's an expensive proposition. Now you can buy a open path methane sensor from Lycor for probably $50,000. Cheap, right? That's why you're right there.
Sure. Bottom right is that one of Shashi Verma's?
Yes. Yeah, this is Shashi's site at called Bob Lake, Minnesota. And I was saying his student that was doing his PhD at the time, Jun Kim, was responsible for running this site. Yeah. Okay, so, but as I say, this is state of the art for landscape level fluxes, right? For whole canopy fluxes. And the program funded by U.S. Department of Energy is called Ameriflux. So if you go to this Ameriflux website, you can find a lot of information on this kind of thing. They just had their annual meeting a few weeks ago in Indiana. The Ameriflux PI held their meeting. So here's their website. You can go here and look at things. Let's see if I can find, oh, here we go. Okay. So there's a whole bunch of information here. And Margaret Torn is the director of the whole program. Let's see, sites. So site search. North America, South America. Here we go. These are the, I don't know how many sites there are, but these are the oh, here we go. So there may be, I don't know, 100 sites in North and South America. Some way up in north in Alaska, all the way down, all over the place. So we have a site in the Sand Hills, for example. Find it. U.S. So this is our sample site near Whitman, Nebraska, at the Gunnison Research Lab. And data is available from all these sites, available to the public. If you want, I think you have to register like your name and email and stuff like that. But you can go and download the data from this site. Actually, this one's got big gaps in it, but you can download the data from this site and do whatever you want with it. there are, there are rules they ask you to follow, acknowledgements and stuff like that, if you're gonna publish data like this. But, it's freely available to anyone. So this is for our Sandhill site, for example, for our windows. If we wait for a minute. Well, let's not wait. When I looked this morning, there was windrows in the center. But, the data are freely available. So here is our, as I said, our Sandhill site, and we have 3 sites up in Mead. Let's see if I can find it. They're called US, NE1, NE2, and NE3. So these sites were started by Shashi, but now they're run by Andy Super, Shashi's student. So here's the NE1 site. The BATM is ancillary data. The overview is a cropland, started in 2001 till now, and you get all kinds of information. But the data are freely available. So you can get latent heat fluxes, evapotranspiration at this site on, I think it's a half-hourly basis, all year round. And play around with it, do whatever you want with it. Latent heat, sensible heat, all kinds of information is available for each of these Ameriflux sites. Ameriflux is part of a larger network, called FluxNet. And this one may take a while. Oh, there it is. So FluxNet is the same as Ameriflux, but it's around the whole globe, right? There are these covariance stations all over the world. And let's not take the time to find the map of where they all are. But you can find out where they are, and you can download data from any of these sites anywhere in the world. So there's Korea Flux, there's OzFlux is Australia, there are these flux stations all over the world. Many of them in China, and lots of them in Europe. You can find out all kinds of information. So, but one of the limitations of any covariance technique is, yes, it gives you what's sometimes called landscape level flux, a large scale flux. But if you're interested in what's happening